All right, so this is class. We are going to go over F and F double prime. You're going to take the quiz. Then we have a lesson on physics and calculus and speed, which is kind of just tying everything together. It's not that new of a lesson besides the relationship of these physics terms that we will get to. We do have a test next class. Okay, I am not in today, but I will be in tomorrow morning. I'll also be available by email tonight, late tonight. So if you have any email questions, you can ask me tonight. But I'll be able to grade your quizzes that you're taking today first thing tomorrow morning. I have your last quizzes graded. Those are going to be handed back to you by the sub. And then you will be given the quiz over this lesson, which you will take home and do. You'll also be given some extra practice problems for speed that you can do. All the answers are going to be online. And reminder, for tests, the way you can study is to do your quizzes from scratch multiple times. I'm talking from scratch. Start them like you've never seen them and do them. And if you can't get any of the problems wrong, then you're setting yourself up for success, okay? So please make sure you do that before the test on Wednesday. Okay, let's start with a basic question. If you're given a function, can you find the points of inflection for the function, okay? Or you can just be asked to examine when the function is concave up or concave down in specific, okay? So I'm giving you a function, boom. You guys can go ahead and tackle this. So go ahead and start, find the points of inflection, examine the concavity. I'm going to do this in the background and not make any noise. You can look up and check your work with my work. And if we need to pause the video, we pause the video. The sub can rewind. Whatever you guys need, you just ask. All right, so we need to examine the signs of my second derivative, take the derivative twice. We need to factor to solve. I factored out a 20x squared. I had x minus 3, giving me two solutions, 0 and 3. Now, when I check my signs, I notice I do not flip-flop signs here. I go from positives to negatives, and then I remain negative. So in this situation, we only have one point of inflection at 3, and we're concave down. Really, when x is less than 3, you could probably not include 0 because this is a location of a 0. So you'd probably say from negative infinity to 0, and then from 0 to 3, knowing that there's no concavity at the point 0. You don't have to be very specific about that. Typically on AP questions, if there's a multiple choice, this would be an answer choice. It wouldn't be both of these answer choices. That would be unfair, and the AP test tries to be fair. I believe this was one of your homework questions. So these are the types of problems that you'd have to do if you were just given functions. We'll look at the quiz before we take it as well together. That way you're prepared for it. So just make sure you have this answer correct. We have 8x cubed minus 8. I believe it's just examine the concavity. I might be wrong. You just get 24x, set that equal to 0 or c when it's undefined. And we get x is 0. We go from the signs being negative to positive. So 0 is a point of inflection. Let's see if there is another question that you had to do with that. Yep, just find the points of inflection, discuss the concavity. Okay, something like this, 14, 16, 12. Those are the ones you're going to see on your quiz. But a lot of questions on your quiz will have graphs. Examples like this. I'm giving you the graph of f prime. Okay, I'm giving you what the derivative of the original function looks like. I don't give you f. Giving you f prime, you should be able to tell me when f is concave down. Okay, ready, set, go. And then you should be able to tell me when f is concave down and increasing. I will do this in the background while I'm quiet. You can look up and check your answers. Oh, and if you're still too cool for number lines, I hope you've gotten rid of that and you've embraced them. Number lines are super important, and they make understanding what's going on easier. All right, and do the next part if you haven't done it already. I might be going too fast, but we can pause. Sub can pause to give you plenty of time to do all of these. When is f concave down and increasing? The easiest way to do this is to just draw two number lines. Have them overlap on top of each other. Because concave down is when the second derivative is negative, right? When is an original function increasing? When is something increasing? When its derivative is positive. So we want to figure out when f prime is positive and when f double prime is negative. I'm going to do another number line. Okay, that's it. -1 to 0. Okay, That's when we are increasing. Our derivative, first derivative of f is positive, and our second derivative is negative. I could give you that same type of question for this. Okay, this is more going to be like a next lesson question with a function, but I could give you the same type of question here. You just have to go back here and also set your first derivative equal to 0, analyze the signs, and then draw two number lines on top of each other, f prime and f. Okay, let's do this one. So here's f prime. One is f concave up and increasing. Pause the video, and then you'll be able to see me do the work, if that's probably a better way to do things. All right, I'm going to set the work. Concave up is when the second derivative is positive. Increasing, when the first derivative is positive. If it was decreasing, then you'd say your first derivative is negative. Okay, but it's not, it's increasing. So I need to figure out when my second derivative is positive and my first derivative is negative. I'll look at the signs of my first derivative first. So f prime is negative when it's left of 0, is positive from 0 to 2, and it's negative after 2. This is the signs of f prime. This is just the values of f prime that I see, the function values. The second derivative, so the slopes of f prime, which equals f double prime. This tangent slope's positive, 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 positive. Tangent slope, that's positive. Tangent slope 0, then tangent slope negative, 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 negative. Think of slopes going up from left to right are positive, down from left to right are negative. We are looking at 1 positives to a 0 to negatives. When is the second derivative positive? Here. And the first derivative positive? Here. That'd be between 0 and 1. All right, f prime, when does f have extrema, maxes or mins? When does f have point of inflection? Same kind of deal here. Next question we'll do as well. So pause the video, and then we'll go over it. Okay, so f has a max here at -2, f has a min at 1, f has a point of inflection at -1. Okay, good. Here's a good question. Now, given the graph of f, this is the graph of f. This is no longer the graph of f prime. This is the original function. They can ask you, when is the first derivative positive and the second derivative positive? They give you a point of inflection. It looks like we have a max at -2 and a min at 0. When is f prime positive and f double prime positive? Well, you could attempt to graph f prime. You could just say, oh, f prime will be positive less positive 0. So I could go positive less positive 0, negative to a 0, and then positive. And then you could graph f double prime from there. So we'd have negative, 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 0, negative, 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 0, positive, 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 positive. And you can see, when is f prime positive? F prime is positive here, it's here, and f double prime is positive here. So we talk about this location here when x is greater than 0. I actually think that's harder than going another way with this problem. Instead, using a number line, I know you guys hate number lines, you think they're childish. If you use a number line, you might actually help yourself out. I have positive tangent slopes until -2. Now, look, f prime is no longer plus and minus, right? This is the function values of f. So I'm looking at the slopes of f for f prime. They are positive until -2. They're negative until 0. And they are positive after 0. Then, what do I do for the second derivative? Well, look at the information that's given to me. We are told, hey, I have a point of inflection here. Well, you can look at the graph and see I'm concave down until -1. So what does that mean for my sine of my second derivative if we're concave down? We're negative. We are concave up after -1. We're positive. When is f prime positive and f double prime positive? Well, we saw it by graphing. I prefer this. It's easier to see. I will make less mistakes right there when x is greater than 0. Okay? So be careful of that. You might be given the graph of f on your quiz today. And let's look at the quiz before you take it. So your sub's going to pass out the quiz right now, and you're going to take it. And then we're going to finish up with the lesson. So let's find the quiz, this quiz. Okay, I start off with a graph of f prime. This is the same graph you saw in the previous quiz. However, I'm only talking about the concavity now when it's f concave up. Okay, so this is f prime, not f. When you're given f prime, when is the graph of f, which you can't see, concave up? Second question, when does the graph of f have inflection points? Okay, so this being f prime, not f, when does f have inflection points? Okay, make sure you use your number lines. That's going to help you. Number 3, order f of 4, f prime of 4, and f double prime from least to greatest. Well, what's important is that one of these is going to be a negative value, one of these is going to be 0, and one of these is going to be positive. You're not going to be able to figure out what the exact values are for all but one value, okay? Remember, f of 4 is the function value. F prime of 4 is talking about the tangent slope. How can you find f double prime of 4? Well, look at the concavity. If you're given f, that'll help you. Number 4, approximate when the graph of f is both increasing and concave up. We just did examples just like that. Use number lines, that'll help you. Number 5, given the graph of g. So this is the original function g. This is not the derivative function. We have a relative max at a, so it's max here, min at c, point of inflection at b. When it's g prime negative and g double prime negative, we just did the problem just like that as an example. When does this have a point of inflection? I feel like we just did that exact problem. So you'll be fine with that. When do we have a point of inflection? Check your signs around your zeros. When is this going to be concave up? Second derivative, see when it's positive or negative. If f prime is decreasing, what information does that tell you about the graph of f? You should be able to figure that out. Remember, when f is decreasing, we said f prime was negative. Okay? Hopefully this helps you out for your quiz. Maybe we'll do this more often. I'm rooting for you guys to do well. I want you guys to do well. I want to help you guys, being my guinea pigs for this class, okay? All right, so go ahead and finish that quiz. You should have passed up your homework to the sub. The sub will collect the homework. And then, sub, why don't you go ahead and pause this video. And when you're done pausing, we will start on the lesson. We will end this video with some of the lesson, and then you will continue on to the next video for the rest of the lesson. Okay, so sub, pause the video now. All right, here's the lesson. The lesson is entitled Tying It All Together in Speed. It's really going to be looking at f prime and f double prime at the same time, okay? We can combine knowledge of f prime and f double prime to sketch f. We can look at a graph of f prime and do a good job of sketching f. We can look at when a function is both decreasing concave up, concave down as well. But what's really going to be important is looking at some things dealing with physics and how some objects could be, moving to the left, moving to the right, be stopped. When is the object's velocity increasing? When is the object's velocity decreasing? When is the speed of the object increasing? When is the speed of the object decreasing? And it all comes down to kind of looking at the relative signs of its derivatives, okay? Well, let's talk about rates of change in physics, okay? You're comfortable, should be comfortable with the differences between position, velocity, and acceleration. Position is just where you're located. Okay? It is a meter mark. We usually use x of t as our position function. Okay? It is not a distance. Okay, sometimes you are given positions in terms of like seconds. So you're given a table and this is seconds and this is the meter mark. You could be at -2, you could be at 5, you could be at 4. This is not telling you that at 0 seconds you've traveled -2 meters. This is telling you that at the 0th second you are at the position of -2 meters. At the 1st second you're at the position of the 5 meters. At the 2nd meter you're at the position of the 4th meter. And sometimes you can give like position functions where you can find, and it's important right here, you don't know what's going on in between 0 and 1. You don't know that you're traveling consistently from the -2nd meter mark to the 5th meter mark. You could be at the half meter mark, maybe at 9. Who knows? Okay, at the half second, at the 9th meter mark. Who knows? Okay, but that's important to know. If you're given a table, you have no clue what's going on in between. But if you're given a function like x of t is equal to t squared plus 2, well, you could plug in any time and you could fill in gaps to any table. If this table is produced by this function, this table is not produced by that function. Okay, so that's important. Well, velocity is given by v of t. Velocity is the change in our position divided by the change in time. Now, the change in our position, and this is our average velocity, and we're used to, before I talk about average velocity, we're used to saying, you know, velocity is equal to your distance divided by time. Well, it's actually not distance. Velocity has a sign. It's actually going to be displacement. Okay, we should know that when velocity is positive, we are essentially, if you're thinking about being on a number line, having an object on a number line, your velocity is positive, your object is moving to the right. If I could just take this object out. Actually, I can in a second. So if velocity is positive, here's my number line, here's an object. If velocity is positive, if I'm on a number line, my object is moving to the right. Or we could say we're moving up on a y-axis. Typically, we go on an x-axis. My velocity is negative, I'm moving to the left. Make sure you write that down. Velocity positive, I'm moving right or up. If my velocity is negative, I'm moving left or down. Okay? Well, velocity is displacement over time. So we could say to find displacement, it's just the change in my position divided by the change in my time. Right? Well, so if I want to find the velocity, the average velocity between 0 and 1 seconds, I would say, okay, my displacement would be 5 minus -2 over 1 minus 0. What is this? This is just a slope formula. This is just slope. I'd say that'd be 7 meters per second. Okay? So I just use slopes of position to find velocities. Well, what if I asked you to find the velocity just at the first second? What's going on just at the first second? Well, the best way to find out what's going on with our velocity given position is to look at the instantaneous rate of change of my position. So really, instead of using a delta, delta stands for an overall change, I can use a d. This d stands for an instantaneous change. And yes, this is just slope. Well, this instantaneous change is tangent slope. Secant slope for average velocity becomes tangent slope. So, turns out if you want exact velocities, which is just your velocity at any given time, exactly what it is, that's just going to be the derivative of your position function. Fascinating. Derivative over my position function is my velocity function. I will prove that to you in just a second. The same can be done with acceleration. It's just going to be the change in velocity over a change in time. Well, this would be the average acceleration. Acceleration, we usually use A of t. This is just, is my position increasing at an increasing rate or increasing at a decreasing rate? How fast is my velocity changing? That would be acceleration. And it turns out it's just going to be the slope of velocity. And if I wanted exact acceleration, I would just have the instantaneous change in my velocity over the instantaneous change in my time, which is just the derivative of of velocity. And I'll show you that in a second. This is super important, super duper important. If I have the position of something, I can find its exact velocity anywhere by taking the derivative. If I have the velocity of something, I can find its acceleration by looking at the instantaneous rate of change of my velocity. And here's how I can prove it. These are two formulas that you are used to seeing from physics. Okay, this is position final, your initial position, your initial velocity times time, 1/2 your acceleration times time squared. And this is your final velocity is equal to your initial velocity plus your acceleration times time. Well, watch what happens if I take the derivative of this with respect to t. Now, we will just say this is x prime of t, okay? Now, this is initial position. This is just a number. This is initial velocity. This is just a number. This is acceleration. This is just a number. If I took the derivative of a number, what do I get? I just get 0, right? Well, if I take the derivative of v times t, a number times t, I just have the number. The t goes away, just like the derivative of 3x is just 3. The derivative of v of t, if v is a number, would just be v. Now, what is the derivative of 1/2 at squared? Well, you take the 2 down, multiply by the half. 2 times a half is just 1, so I'm just left with at. Oh my goodness, by taking the derivative of this, I got that. It's incredible. You didn't know that at all, but now you see it. Instantaneous rates of change of position will give you exact velocities. If I look at my velocity, why don't we take the derivative of this? What happens? Well, v prime, this is just a number. A is just a number, is just going to be A. Well, why is it just A? Why isn't it just something other than A? Because you're used to an A being a constant, and your A always being constant in projectile problems. And this is the projectile functions that we were talking about. A in physics was typically gravity. And you knew it was always negative 9.8, right? Well, there you go. The derivative of your velocity, acceleration, is always that, okay? So that just shows you this relationship. You will be given situations where you're given position functions, and you'll be asked to find the instantaneous velocity, instantaneous acceleration. What is the diver's velocity when t equals 1 if its position function is just that? Well, velocity at 1 is just going to be the derivative of position at 1. The derivative of position is negative 32t plus 3. I plug in 1. It'll just be negative 32 plus 3, which is negative 29. X of t is in meters per second. This would be the change of position with respect to the change in seconds. That's how you get meters per second. Change in y over change in x. What is the instantaneous acceleration? Well, acceleration at 1 is just going to be the derivative of velocity at 1. The derivative of velocity is negative 32. This would always be your acceleration. This would be the change in your velocity per second. That'd be meters per second, which is why we typically have meters per second squared. Okay, that is the introduction to the rest of the lesson. We're going to watch the other part of the video for the rest of the lesson. A lot of it is sketching f given f prime, using f and f double prime. Make sure we get to speed when something is speeding up and slowing down. and also make sure we get to some other straight line motion problems. Your sub will give you the quiz as well as some speed homework problems. You are to definitely do that to study for your test. Don't forget, study for your test by doing your quizzes from scratch multiple times. I believe in all of you. You all are capable of getting hundreds on all of these tests, okay, including this next test. If you do your quizzes multiple times, you'll be prepared for these tests. All right, let's go ahead and start the next video.